So first of all, thank you so much for coming today. I think it's the first day of the new semester, is that right? Yeah. So you really should be out drinking Czech beer, and you turned up to listen to me speak, so I'm very grateful for that. I wanted to start just by saying what I'm hoping to do today with this talk. So I want to talk a little bit about the company SwiftKey, to give you a bit of context for that. And then I want to talk about the technical problem that we solved, or that we tried to solve when we started the business. But actually, more than both of those two things, really what I want to talk about is how you go about taking an idea, or taking a problem, and applying the scientific method to solving that problem for real people in the real world. And I think it's quite pertinent, actually. We were chatting before the lecture about the need to take real world problems and to take students who have bright ideas and to bring these things together. And I think one of the saddest things in the world of science and technology is that there are so many great ideas that are in universities but that don't make it out into real people's lives. There are too many technologies that are waiting for a problem, rather than people starting with a problem and then coming up with a way of solving it that really connects with real people. So that's the meta argument that I want to make today. Okay, so I'm going to start just by racing through some context around the company, to give you a bit of a background for what SwiftKey is. When we founded in 2008, we had this vision to license our technology to the major mobile manufacturers, so you know, the Samsungs and Sonys and so on. And so we kind of knew from the start that we were going to have to be a global business, even though we were based in London and working from our bedrooms. We knew that we had to have at least a global mindset if we were going to have any chance of licensing the software to these guys. My own background is in applied natural language processing and machine learning. And just out of interest, if I was to say NLP to you guys, how many of you would know what I was talking about? Okay, a few, that's fine. And what about machine learning? A few more of you? Okay, cool. So natural language processing, more and more of it, I think of it as machine learning applied to problems that involve human languages. And machine learning is therefore a broader field that looks at the tools and techniques that are used to solve a class of problems. And I refer to these as inference problems. So essentially problems that are not amenable to traditional software engineering approaches. And in machine learning, we set up a framework, and then we allow the data to parameterize that framework so that we can make predictions about data. And this should become clearer in the context of what we try to do at SwiftKey as I go through the talk. Innovation is really the heart of our company. So people work for us because they want to solve difficult problems. I think my microphone just sort of slipped down the inside. And finally, we're very much mobile focused. So I think mobile technology is the area of the industry that is particularly exciting at the moment. There's so much stuff going on, so much scope for innovation. We currently have about 110 staff, and we're split across London, which is our HQ, and we have offices on the west coast of the States and also in Seoul in South Korea. I talked a bit about the innovation that drives us, and to that end we've ended up hiring quite a lot of fairly high-powered engineers. So we have, I think now, 17 or 18 PhDs, and these are mostly focused around the areas that I was talking about, machine learning and natural language processing. We've been finding patterns for a while, and we do this quite cool thing where I guess it's a little bit inspired by Google's 20% time, but we do it slightly differently. So every 2 months we take the whole company to a completely different location, and we spend 2 days working on whatever people want to work on. And this has inspired some stuff that is sort of completely outside of the scope of our business. So we're essentially helping people to type on smartphones, but the guys have built things like an AI for deciding how tea is made and distributed within the company. So she's called Mrs. Doyle, and she's a Google chat bot. And basically you tell Mrs. Doyle if you want tea, she's listening until there are a number of people who want tea. Everyone's obsessed with tea in England, you probably don't understand it here. And then when there's enough people, she then decides that one of those people is going to make the tea this time, and she sends them a message. So it's sort of an interactive way of making tea. It's outside of the core business, but it's the kind of thing that people just decided they wanted to have a go at building. And I think this is one of the things that helps keep us fresh within the company. You know, however interesting a problem is, once you've been looking at the same problem for a while, it's really refreshing to think about something different. So why did we set up the company? Well, basically, we wanted to solve the problem of typing on touchscreen phones. In 2008, the iPhone had been launched a year earlier, and we could see that there was going to be this explosion in the use of smartphone technology. And in particular, people were going to use smartphones more and more to communicate through text. And it's, you know, the phone obviously was developed for communicating through voice, but more and more as time has gone on, the various methods of communicating via text and other media have exploded. So we could see this was happening. We could also see that people were struggling to type, particularly those who were used to coming from physical keyboards. And so what we wanted to do was to start from the ground up and build an engine that would solve this typing thing in a better way than had been done in the past. And a bit later I'm going to come back to this. I'm going to talk about actually how we went about doing that. So I'm going to move on from now. So we built this piece of technology, and we were finding it really hard to sell. We put together quite a lot of presentations that showed the metrics we were getting out of the engine were significantly better than existing text input solutions. But the reality is, when you're talking to execs in big mobile companies, they're really unimpressed by numbers. They basically want something on a phone that they can look at, that they can try out, that actually, that's what gets them excited. So we decided to build an application. This was in late 2009, early 2010. And out of interest, how many people here have Android phones? Good Lord. How many people don't have Android phones? Okay, maybe the nature of this talk slightly biases things, but when we started, Android had 1% of the smartphone market. But we could see that a number of these major players had signed up to the Open Handset Alliance, and we could see that it was a great opportunity to get something into the hands of the decision makers in these companies. Now, of course, 3 years on, almost 4 years on, Android stands at about 70% market penetration, which is a phenomenal growth story, obviously, in the last few years. But we really didn't think of this as a consumer product. We built it because we wanted to be able to leave these execs with something that they could actually try out with their own hands. And then when we actually did launch SwiftKey, we had such a great reception from Android developers, from people who were part of this young but growing ecosystem, that it became a product in its own right. And one of the things we learned through that process was actually, for us, we found it a lot more fun building products to sell or give, or however you monetize it, directly to consumers, rather than licensing to manufacturers. So our real passion has become building products for consumers, although licensing is still a big part of the business. If you've never seen SwiftKey, this is just a really brief overview of what it does. Basically, it's a keyboard, and it has these 3 candidates that sit above the keyboard, and it tries to guess what the most probable thing that you're likely to say next is. And we arrange the interface so that the word that's most probable is right there in the middle. And I remember actually the conversation that I had with my co-founder where we came up with this principle of, you know, if predictions are going to be powerful, we really need to put them in the middle of the interface. And we were having lunch in a restaurant just down the road from my parents' house. And what I find so interesting about thinking about that conversation is that now I think there are somewhere between 250 and 300 million smartphones that use that principle of putting the main candidate into the middle. And that all stemmed from that one little chat we had over lunch. So one of the things we did with SwiftKey was we thought, well, previous next word prediction systems had basically been simply frustrating because the amount of time that they got the word right was so low that for practical purposes it wasn't really any use. But what we believed was that if you could get the accuracy high enough, that actually you could offer people a different way of typing. So rather than predominantly typing all of the characters, you could actually select words and build up your sentence, particularly for the kind of language that you would use a lot when you're using your smartphone. You could actually build up sentences by picking words and then by sort of prompting the prediction engine by using the characters. And what we found was that actually quite a lot of people really did like this. It was a completely new way of typing. And that was very exciting for us to see that. But what we also realized that there's a large number of people who didn't want to type like that. They wanted just to sort of mash away at the keyboard and have the software correct their mistakes. So we also then spent quite a long time working on the correction engine with SwiftKey. So that's the other thing that it does. Another thing that we thought about from the start was multilingual users should have a better way of typing than was offered. And so the idea that you should have to manually switch language while you're typing was something we believe was fundamentally flawed. And out of interest, how many bilingual people do we have in the room? So you must be all at least bilingual, right? How about more than 2? Okay, so let me explain what that means. So if you speak more than one language, put your hand up. Okay. Sorry, that's what bilingual means. You got me worried there. So what we felt was that if you speak in more than one language, you shouldn't have to explicitly change the language of your keyboard. It should just predict the language that you're using. So we built a system that detects what language you're typing in and then predicts text in that language. And then if you switch, it starts predicting in another language. We recently launched something called SwiftKey Cloud, which is basically everything we're doing here is learning a language profile that represents the way you express yourself. And what SwiftKey Cloud does is it just stores that so that whenever you go to a new device, you have the same experience. I can come back and talk a bit more about that later if people are interested. So basically the company has this app on Google Play, and we also license technology to mobile manufacturers. We have some good relationships with the media, and the app, as I said, it was kind of a surprising success to us. I remember the very first day we launched, and just following on Twitter all of the feedback. And so SwiftKey's now been the #1 paid app in 58, I think that was the latest number, 58 Google Play territories. And I think it's currently #1 in 35. And for me, this was probably the most exciting day of my sad and lonely life. So yesterday I was talking at USIS, the science competition for youngsters, and tragically I asked how many people had heard of XKCD, and about 3 people put their hand up, and Thomas was one of them. But I'm going to try it again today. How many people here have heard of XKCD? Okay, that's much better. But you are a bit older, so that's good. So we had an XKCD written about SwiftKey, and actually I was giving this talk 3 or 4 days ago, and someone said to me, have you read the alternative text on XKCD? And I had no idea what he was talking about. Turns out, every XKCD comic has alternative text. So right, put your hand up if you knew what XKCD was, but you didn't know that it had alternative text. Wow, not very many people. Okay, I didn't know. Apparently it does, and it's great. Great, so what I'm going to do now, hopefully that gives you a brief overview of what the company does. I'm going to tell you our story very, very quickly, and I'm going to show you a few photos as well. So 2008, we had this idea. My co-founder John was working in the civil service in the UK, and he had seen a lot of people struggling to type on smartphones. At the time, I graduated from university in England about 18 months previously. I've been building systems that were based around the use of NLP and machine learning to solve particular tasks. And I had actually done some research in spam filtering, where basically the idea was, if you can model the way people use language in spam, and you could model the way people use language in non-spam, then you could build a classifier from this and essentially filter out all the spam, which was a huge problem back in the early 2000s. But more particularly, one of the things I found out when researching spam filtering was that if you model a huge data set of spam, and then you model a much smaller focused data set, so let's say just the messages that one person has received over the last couple of months, and you do that for genuine email as well, so you take a huge background data set of everybody's genuine email, and a smaller data set of the specific email that you've written, and then you combine these models, you get something that's actually more powerful than if you lump all of that data together, or if you just take one or other of these data sets. And so that principle was the first kind of technical insight that we built SwiftKey on. And the principle was, if you gather a huge amount of data about the way a lot of people use language, and then you gather a much smaller amount of data that's focused just on the way one person uses language, and then you combine these two models, that gives you something that's a better predictor of language than either of those two things in isolation, or of all of that data lumped together. So we had that idea, and it took us about 18 months of building the background technology, going around pitching things to people, and what we discovered was that it's really hard work to take a concept and sell it to people. So these are my first photos. This is me and my co-founder. He's the good-looking one. That was actually our first sales trip to Asia, so that was in Taipei. And on the right, that's me. I know I've changed beyond recognition since then, but that was my Christmas holiday, and I was writing a patent application on an enormous laptop. And one of the things we realized when we started was that intellectual property was going to be really important to us. So we knew that this field of predicted text had a lot of litigation in the past. So we spent essentially about half our money for the first 12 months or so filing patents around the model. We felt that was necessary, particularly because of the nature of the space we were in. There's a debate to be had about how useful patents are in practice, but they're a good way of growing the value of a company, from the perception of investors at least. 2010, we launched SwiftKey for the first time, and we signed our first licensing deal with a very small UK-based phone manufacturer. And then when we signed that deal, we had only 4 people in the company, and only 2 of us were technical, so we had to really work very quickly to hire people to build a keyboard to actually deliver as part of this contract. And the first guy we hired to work on the keyboard was a Czech. He's sadly now left, but there are still remnants of his exceptional work in the product. So if you use SwiftKey and you go to the secondary pane with the numbers, that was his layout. You should be proud of yourselves. So we went to the Mobile World Congress in 2010, and we pitched this early product, and it was in such a bad state. I think I spent most of the conference behind the stand trying to hack the code into a state where it would actually work. This was our very first office. We had, I think, 10 people. Oh, there's the Czech guy, the guy with the long hair. I've seen some people on this trip who look very much like that. For instance, this gentleman here. Very good-looking guy, Adam was. 2011, we grew from about 15 people to about 30 people. And by now, we started to feel like we were beginning to grow as a business. And SwiftKey was by now a pretty well-recognized consumer product. And I think towards the end of 2011, we had built up enough language coverage to really start pitching to some of the big guys like Samsung and Sony and BlackBerry and Apple and others. But one of the challenges for us was, if you're going to sell to somebody like Samsung, you have to support a global range of languages. So we had to support at least sort of 55 languages. And that was a big upfront investment that we had to make. But actually, the fact that we had the consumer app really helped us with that, because we were able to use some of the revenue that we generated from that and some of the traction in order to create a story that we could go to some of these guys with. I talked about innovation days. This was us in our next office, having a great time, going around looking at what people had built on Innovation Day. In 2012, we grew from 30 to 90 people, so it's a big growth curve for us. We founded offices in the US and South Korea. And we finally sort of went over that tipping point where now we were taken seriously, whereas, you know, for the first 18 months we were just 2 guys and no one took us seriously. Finally, by the time we got to this point, we had a great consumer story, and I think more than anything else for us, in terms of the development of the company, it was the consumer story that made all the difference. And if there are any of you here thinking about starting a business, or perhaps you're already running a business, there's nothing persuades the market like a consumer story. So the fact that people were saying, this is a great product, you know, I would replace my keyboard for this. The reason we charged for the app is because we wanted to show the manufacturers that people would pay $4 to replace a keyboard that was already there. So that consumer story was absolutely critical. And these are just a few other random photos. This is the SwiftKey Frisbee team up the top, up there. This was us winning an award. Exactly 2 years after we launched the app, we went back to Barcelona to the Mobile World Congress, and we won the Most Innovative App Award. This was us being silly on April Fool's Day. We really took a leaf out of Google's book here, and we built this thing called SwiftKey Tilt, which was great fun, actually. We had a lot of fun. just being silly. So if you want something to do this evening, Google SwiftKey tilt. It's quite funny. And it features me dancing. This picture here is our current office. So just to give you a sense for that. And this is us in 2013. We expect to hit about 150 by the end of this year. Okay, I just wanted to give you a feel for some of the numbers. So the slightly confusing thing here is that we have two business models, because we have the app, which we sell to consumers, and we have the licensing model. From the app, we collect these statistics about the number of characters, sort of on average, that people have entered, and we reckon we've reached somewhere around the 2 trillion characters stage now, and we've saved people about just over 500 billion keystrokes. And we estimated this in terms of typing time, and we think we've saved the world about 7,000 years of typing time. So I'm going to write that on my grave. We expect that there'll be about 150 million devices using our technology this year. So that means a combination of people who've downloaded the app and people who are using the software because it's licensed to people like Samsung and Sony. Okay, I'm going to stop there for a minute and just see if there are any particular questions related to the kind of business side at this stage. I'm going to stop again later for more general questions, but I'm about to move on to more the technology side. So if there are any, yeah.
Yeah. What was your main motivation to open other offices in other countries?
Right, great question. So why did we open offices in other countries? So the reason we opened an office in South Korea was because our major customers, in terms of the mobile manufacturers, are based there. It's really interesting what's happened in consumer electronics. On the hardware side, the momentum has really shifted from Japan to South Korea, particularly in mobile. So for us, we need people on the ground working with Samsung and others. So that's why we did that. The west coast of the States, in terms of the software side, that's where all the heart of mobile software is. So it's really interesting. Basically, you've got these two locations completely on the opposite sides of the world, and we're right in the middle, so it's a bit of a nightmare from a time zone perspective. But software is all about the west coast, and hardware is currently all about South Korea.
Yeah, thank you.
Yep.
I had a question. You didn't mention any investors. So is your company purely self-funded, or?
I wish. No, it's a good question. So we did a number of rounds. We actually just closed a round a couple of months ago with a European investor called Index Ventures. We've done probably altogether we've probably done 5 rounds, I guess, but most of the early ones were really small friends and family rounds. So I think total we've probably raised maybe $25 million.
And did you say the last round was from European investor?
Yeah, Index are a sort of pan-European investor, but they have quite a presence in the US as well. Yep.
From the perspective, do you think it was quite necessary to have a patent systems to cover for law of the inventions, or it was not so necessary?
So the question is, was it necessary to file all these patents?
For you to patent your technology.
Yeah. Was it necessary for us to patent the technology? Yeah, it's a good question. So I think the whole patent system is just a game. I think there's very little value that comes out of it. If you look at why the patent system was set up in the first place, it was actually set up as a way of persuading people to divulge their inventions, so that the pace of technology would not stagnate. And what it's become is a way of protecting inventions. And unfortunately, the people who can protect them are the people who have enough money to pay the lawyers. So I think if you're building a a technology business, where the heart of the value of your business is in the technology, having patents is simply a way of saying we do actually have something that's valuable. So I think for us, for instance, it helped a lot in terms of getting investment for us to be able to say, oh, we've got 5 patents pending. In terms of the actual value to the world that has been created by us patenting technology, it's very small. It's a game that you have to play if you're in a certain technology space. But I think it's changing a bit, and I think it probably, I hope that in 20 years' time, our way of protecting IP will be totally different, but it might not be. Any other questions? Yeah.
You didn't seem like you had good experience with the investors. Did anything went wrong?
Why do you say that?
You just seem like not really content with the. You said like, I wish we were.
Oh, sorry. Okay. I only said that because then I would own a lot more of the company. So that's purely selfish. No, we have had good experience actually. Yeah. I think the reason you take investment is 2 things. Partly, obviously, for the money, but equally important is the network that investors bring. So, if you get a really well-connected VC, then the reach that you have through that is of fundamental importance. Yeah.
Why do you need so many people working on just a single keyboard?
I wish we didn't. Then I'd be able to pay myself more. So this is a question we actually get quite a bit, and it's interesting because all text input companies in the past have been in the order of about 80 to 120 people. And the reason you need that number of people is because the range of language support, so we currently support 72 languages, I think, and in order to build up that kind of breadth of experience across all those different languages is quite costly, even though our approach is heavily data-driven. So, you know, there were versions of SwiftKey in languages that went out to sort of user testing where nobody who spoke the language had ever actually seen the solution in development. But even so, that still takes a lot of people to do all the QA and all that kind of stuff. I think the other thing is that, for instance, if you're building a piece of software that's going to be licensed to over 100 million devices, the amount of effort you have to put into making sure that that software is engineered in a rock-solid way, that takes a lot of resource as well. So, and I guess the other thing is that we've always been working on other projects that surround this. So we're growing fast now, not because of the input, but because of some other things that we're doing, which are quite exciting, but are going to require some investment. Any other questions? Yeah.
So recently the database was built in my phone, right? And now it's kept in some cloud or whatever. What about NSA and this kind of stuff? I wish I could drop Gmail and use my private service or whatever, and then I type my emails on my cell phone and everybody will again know.
Yeah, so the NSA are paying us very well for the new product. So yeah, essentially we have a number of opt-in services that use the cloud, and one of those is called personalization, and that's where you essentially allow the software to analyze your historical text from various online services, so things like Twitter, Facebook, Gmail, Yahoo, etc. That builds a model that then gets pulled down to the device. The backup and sync service, which is also part of the cloud services, that was what I referred to earlier on, where it takes that profile, the language model that has been built that captures the way you express yourself, and stores that on our cloud-based servers, and then synchronizes it between all your devices and stores it in the case, you know, where you lose the phone. Basically, none of those services you have to use, but you can use them if you want those benefits. We haven't been approached by the NSA yet, but obviously we're waiting for that phone call. Any other questions?
Is there some company in competition with you for Android platform?
So, do you say, are there any other companies?
Yes, developing the same software for Android.
Yeah, so there's a big company called Nuance, who are based in the States, and they acquired a company called Swipe, who were our main competitors for sort of most of the last 3 years or so. So Nuance were already the major player in text input software, and they continue to be. They're also heavily in voice recognition. And what we see is probably, on average, maybe once a week, there's a new company that starts up building a new type of keyboard. So there's a lot of people interested in getting into this space, but in terms of existing market competition, it's really only Nuance. Anything else? Okay, cool. I'm going to move on. So now I want to talk a bit about how we went about building the technology, and what I want to get across here is essentially an approach that says, what's the problem, and then how do you design technology to solve that problem? So I'm going to talk about text entry and how you characterize text entry as a problem that people have. And I think the traditional approach to inference problems, and this is the type of problem that I referred to earlier, and it's the type of problem where the number of parameters that you need to solve that problem means that it's too complex to use traditional engineering methods. So it's too complex just to sort of write a program that does it. And the interesting thing about typing is that before smartphones, and before touchscreen phones in particular, typing wasn't really an inference problem. So if you can assume that there's a one-to-one mapping between the action of touching the keyboard and the character that gets displayed on the screen, that's a traditional engineering problem. You know, the problem is how do you turn a keystroke into a character. As soon as touchscreens became ubiquitous in the input market, then it really changed the game completely, because there's no longer a one-to-one mapping. So you don't know with confidence whether what somebody, you know, the character that somebody typed is actually the character that they meant. And what that means is that it introduces a layer of guesswork. And inference, making an inference is basically the same as guessing. So inference technology, inference problems, are problems that involve a certain amount of guessing on the part of the software. So you have this new world of typing where you've got touchscreens, and now it's an inference problem. But how do we characterize that? And again, perhaps a traditional way of thinking about this would be, well, we know that the software is going to have to do spelling correction. So we should build a module that understands how to correct spellings. We know, for instance, that we want to be able to complete words. So we should build a module that understands how to complete words from a given prefix. And there are various other modules that you then sort of bolt together in this framework. And the thing about inference problems is that that's almost always not the right way to go about it. So what you want to do is to create a framework, a mathematical framework that allows you to solve the problem. And it allows you to solve the whole problem. So the goal here is to try and come up with a way of characterizing the particular problem that you have in a way that if you could do it well, would solve the problem completely. So I'm gonna talk through some thoughts around this. I know some of you have a lot more experience with these types of approaches than others. So for some of you, this will probably be way too simple, and for some of you, it will probably be too complex. So I'm trying to hit a sort of middle ground, but feel free to stop me and ask questions if you want to. So what I've shown on the screen here is a way of characterizing typing in the language of probability theory. And what these symbols stand for is, I'm interested in the probability of a sequence given some evidence and a set of models. So S stands for sequence, E stands for evidence, and M stands for models in this case. And what I'm trying to say here is that basically the user has a sequence in their head, and they're trying to get that sequence onto the phone. And the inference here, the guesswork, is for the software to guess what that sequence is. And in order to do that, we're going to use any evidence that the user has given us. And we will already have trained a set of models that allow us to interpret that evidence in such a way that we can solve this expression. Now, what this expression does is it says, over all of the things that a user could possibly want to say, I want to have a probability distribution so I can choose the one that's most probable. Or in fact, in this case of SwiftKey, I want to choose the one that's most probable, and then the two ones that are the next most probable and the next most probable. So this is great. You know, I think we know that if we could solve this problem perfectly, and we had perfect information, then basically we could build a typing system where all the user had to do was just keep tapping the middle button and it would get it right every time. Now in reality that's quite difficult to do because both the quantity of evidence and the interpretation of the evidence leaves us having to make a guess, which is where the inference comes in. And the question is the guess good enough to be useful? Because if it's really bad, and if we do a really bad job at solving this problem, we know that we'll do a really bad job at building a typing engine. But what's also interesting about this is that the features of the software are going to come out of this expression. So I just want to write a couple of things up here on the board. So here's the expression that I'm going to start with. And I'm basically going to ignore the M because I'm just going to assume that we have these models that we've trained in the past. And then I'm going to do a typical thing which probability theorists love to do, which is to use Bayes' theorem on this to turn it into something different. How many people have heard of Bayes' theorem? Okay, take my word for it. Okay, so what I've done here is I've taken our original expression which said I want to estimate the probability of a sequence given the evidence, and I've turned it into four other entities that I need to estimate. This one is the probability of the context given the sequence. This is the probability of the input given the sequence, and this is the prior probability of the sequence. And I'm just going to explain what I mean by those things. So let's say you've typed dear and you're trying to type Ben. Okay, so let's say you type B and then you type O because you made a mistake. The way typing systems work, you can essentially divide this up into the thing that you've already typed and the thing that you're trying to type. So this is the context, and this thing that you're trying to type here is the input. And if you think about this is a sequence of characters. This, if you think about typing on a touchscreen phone, this doesn't necessarily need to be a sequence of characters. It could be a sequence of touch points on the surface. But what I've essentially done is to split this up into two things, two different pieces of evidence. One is the context and the other is the input. That's the C and the I. And then the prior probability over sequences is essentially our best guess before we've seen any evidence about what is likely to be the most probable sequence. So, I want to move on to the next slide, and I'm going to come back to some of this and hopefully paint a picture that will make some sense. So there are different interpretations of this. So I've essentially, in order to do this, I've actually made an assumption. I've basically assumed that I can split up these two things and that they're independent sources of evidence. And what that means is these two expressions are going to be contributing separately to solve this main expression. And what I've done is made an assumption that's not true. So in reality, the context, which is here, and the input are not at all independent. So it's very likely that my input here is going to be correlated with my context. And in fact, I'm going to need it to be, because that's what I'm going to use to guess what the next word is most likely to be. Now, there are other interpretations of this. Okay, I've got these three quantities, and I'm talking about a probabilistic interpretation here. And that's what this first point on the slide is. And I'm going to explain what I mean by the smoothing parameters in a sec. But another interpretation of this is actually that these values are just signals that are coming from the user. And I need to learn how to combine these signals in order to give me the best overall ranking. And typically the way I might combine these is by using a type of machine learning algorithm called a rank preference learner, for instance. So you can imagine that some weight will be assigned to this quantity, and some weight will be assigned to this quantity. And I'm going to learn those weights by essentially looking at data and then optimizing the outcome for this expression. Now, another way to think about this is actually to try and solve this whole thing as one problem. And this is probably the hardest way to do this, from the perspective of the amount of time that it's going to take me to train the software to learn how to solve this problem. But the benefit of that is that I don't have to make these assumptions about splitting up these things. And for those of you who have a background in machine learning, using something like a maximum entropy approach, where I can express all of the different pieces of evidence as features within a single framework and then train it, might be a way that I would go. In SwiftKey, we take the first of these approaches, which is basically the easiest. And one of the themes going through this is going to be that when you're building a piece of software for the market, the thing that you have to bear in mind is not what the best approach is, but what the best approach given the constraints that I have. So when you're building something to use on a phone, you know, there are things that you just simply can't do, constraints that you have that you wouldn't have if you were using a server farm. And so we always have to be thinking about that. What's the best thing that we can do given the constraints that we have? We make this assumption that these two quantities are independent, and then we estimate these distinctly. And for those of you who have some knowledge of probability theory, what we can do is we can use how much we smooth these distributions as a way of governing our degree of belief in each distribution. So in other words, if we decide that we don't actually really believe the input, so we have a very weak signal from the input, we can smooth that very heavily. And that means that the context in this expression is going to dominate. Okay. So I said that at SwiftKey we took this first approach. What that means is that we're going to estimate each of these distributions separately. And the first one we're going to look at is this one, which is the context model. So I'm going to do a little bit more maths here. Perhaps I could stop for a second and just ask if anybody has any questions. I think that will make this clearer. Yeah.
I would like to ask which part of the equation is based on the specific user history,
yeah,
or my personal profile?
Yeah, great question. So the answer is both of these parts. So this is dependent on your language history, and this is dependent on your interaction history with your phone. And I'll explain how that happens. This term here, which I haven't talked about yet, this is simply a normalization term. So basically, we're going to forget about that. So the way that most people set up problems that they're going to solve, probability theory, is they write down an equation and then they say we're going to ignore certain parts of it. And this is very, very hard to estimate, so we're going to ignore it. There it goes. There's a problem with ignoring that, but we can talk about that later if you're interested. Okay. Any other questions? Cool. All crystal clear. Great. Okay, I'm going to take this expression here, and I'm going to convert it again, and I'm going to do it down here just so you can see what I'm doing. So I'm going to use Bayes' rule again to make this look like this. Okay, now, the reason why I think this is interesting is because it shows how the interpretation of the mathematics gives you a function within the software. So I'm going to talk you through what this means now, okay? Part of the reason I've done this is because this is the probability of a sequence given the context. Okay, now this is a classic language model. So I'm interested in I talked about this context dia, okay? So I'm interested in the probability of some sequence given the word dia, okay? And what I'm doing here is I'm essentially choosing candidates. So I want to do this over all the candidate sequences that I have, which unfortunately is an infinite set. But there's a way of narrowing down that set. And one of those candidates might be my name. So I want the probability of Ben given dia. And what this means is, how likely is it that Ben is going to follow dia? Now, there's another term here which is pretty interesting, which is the probability of the context. So the context here is the word dia. And at this point, I'm going to make this a little bit more complicated, because when I say a sequence, the user is interested in a sequence, that user may actually speak a number of different languages. And if we just take the sequence on its own, that's actually not enough. So let me give you an example. If I take this word, so those are two different words, but what you can't see is that one of them is English and one of them is French. So this is the word for bread in French, and this is the word for hurting yourself in English. And what that means is that in order to differentiate these, I actually need to pair these with languages. So what I'm going to do is pair each of these with a language. So whenever you see this S, it's actually both of these. Okay. And if this is a word in English, then the models that I've trained are also going to be the English models. And if it's a word in French, then the models are going to be the French models. Okay? So when I estimate this, what I'm actually doing is I'm saying, what's the probability of the context sequence given the model that is related to this sequence? Now, this is language detection. So what comes out of these equations is one expression that gives you this feature in software, which is the language detection. So in other words, if this is a lot of English words, then it's very probable that this term will be high. If it's a lot of French words, then it's probable that this term will be high in the context of a French word. In the context of an English word, it's very likely that the probability of this is going to be low. Now, the reason this is important is that it essentially favours words that come from the models of which I've seen lots of words in my context. And so what that does is it essentially picks the language that I'm typing in at the moment and will try to predict a word that follows in that language. And this probably isn't particularly clear at the moment, but the point is really that all of this comes from one expression. So the functionality that we implement in the software, and what I've done here in this slide is just to pick out some of the features of the software and show you how they all flow back to this one single expression. And the benefit of this is that we can make some estimate of how well we're doing at solving this expression by choosing some performance metrics that give us a handle on that. And then we can see how if we tweak this bit of functionality, what effect does it have on the problem that we're actually trying to solve. That's the reason we do this. Okay, so I already talked a little bit about this, and what we're doing here is using language models to capture different linguistic domains. So I talked about different languages. I also talked at the start about how combining very focused language with more background language is something that is very powerful in predictive modeling. And so what we're actually doing here, when we make these estimates about the context, is we're actually combining models. So I'm taking a model that is a language model, a language-specific model, so English or Czech or whatever it is. I'm taking a conversational model, and I'm taking a user model, and I'm going to combine all these three using some function, which could be to choose simply the model that has the most confident guess, or it could be to interpolate these estimates in some way. And I'm going to give you just a high-level overview of all this, and then hopefully stop with enough time to look at specific areas if you're interested. What kind of language models work well? Well, smooth n-gram models are very fast and efficient, and work well with standard kind of try-search techniques. So what we've done to date in SwiftKey is focus on n-gram models. And again, this is partly due to constraints, partly because we have a lot of data, and n-gram models, it's very hard to beat an n-gram model when you have a lot of data. But you need to smooth the model. What do we do? Well, you can do various things to smooth language models. We actually do something that was proposed by Google, which is called stupid backoff. And what Google showed was that if you have enough data, it really doesn't matter what technique you use for smoothing. You can do something really, really simple, and it works as well as anything else. But there are all kinds of other interesting things that you could do. So at the moment, we're doing some work to look at neural network language models, which are really interesting, related to the field of representation learning and deep learning, if you're sort of in that space. And what's really interesting about neural network models is that they're able to learn the semantics of terms as well as just their sequentiality. And we also have this intuition that because in a neural network, essentially the statistics or the knowledge about individual entities is shared across the network. And this helps you actually to be very efficient in principle. So we think that it's possible maybe to embed some of these models on the phone, but we'll see. So now I'm looking at this bit, which is input modeling, which comes down to the question that was asked over here. So the interesting thing about this is that it's a totally different modeling problem. So basically, we're interested here in, if I've touched the screen at this point, and this point, and this point, what's the probability given a particular sequence? So basically, the way I'm going to interpret this expression is I'm going to say, I'm going to choose a target sequence. So let's say my target sequence is Ben. I'm then going to look at my keyboard, and I can see that the B is down here, and the E is up here, and the N's down there somewhere. Is that right? Yeah. So let's say I have 3 touch points, one there, one there, and one there. So the probability of this expression in this instance is going to be really pretty low. Whereas if I have a touch point here, and obviously the order matters here, a touch point here and a touch point here, then it's going to be pretty high. So how do we model this? Well, what we want to do is every time you as a user aim for the A key, we want to collect all of those keystrokes. And let's say that forms a cluster of strokes somewhere around the A key, like you can see here. We then want to model this in some way as the probability that when you're aiming for a particular key, that you hit in a particular location. So we can then model the fact that your perception of the keyboard might be quite different from how it's actually laid out on the screen. So what kind of probability distributions can we use to model this? Well, Gaussians are a nice choice because they're very simple to estimate. But there are lots of other things. I mean, we already have to take account of the fact that the spacebar is not really a sort of circular distribution, it's lengthways. So we use a Gaussian stretched across a line for that. But there may be other distributions that are better. You can imagine if you actually model the key, it would look a bit like a Gaussian with the top chopped off. And maybe that's a better way of modeling it. So we have to train these models, and we use something called maximum a posteriori training, which basically says we already have a prior which is set over where the keys are located on the keyboard, and then we're going to allow the evidence to modify that prior. And the slightly complex thing here is that we need to capture a lot of training samples. So we need to know, for instance, that when somebody typed a W and actually chose the letter E, we need to keep that mapping so that we can correlate each of those touch points with a character on the keyboard. And that gives us this set of touch points which we can then fit using map estimation. That gives you something that looks kind of like this, and if you use SwiftKey, there's a feature, if you go into stats, you can visualize the heat map, which we call it, which is actually the probability distributions that sit underneath the keyboard. And in this case, you can see that these are the priors here, and this is what happens after about, I don't know, about 100 keystrokes. So these start to adapt. And it's pretty interesting to see where the trends are. So maybe you always hit to the left of the key that you think you always hit on. So we also support a continuous model, which is where you drag your finger across the keyboard. And you can kind of use the same principles here, so you extract features from the continuous stroke, use similar distributions to tie those features to characters in the keyboard, and then we compare to an idealized input. So hyperparameters are the parameters that govern the higher level characteristics of the model. So for instance, in both of these cases, these distributions are going to have a smoothing parameter. That would be considered a hyperparameter. Whereas the actual statistics about about words following each other, those are the simple parameters of the system. So we have lots of hyperparameters in our models. Some of them we have to set manually, some of them we can learn. So a good example of this is, if you think about how you type, if you're the kind of typist who just mashes their thumbs at the keyboard and presses space and relies on software to correct your mistakes, then the probability that you are going to look at a word and select it before you finish typing it is very low. And what that translates to is the probability that we should show a completion of a word from a prefix for you, if you're that type of typist, should be very low. Whereas if you're the kind of typist who taps out quite carefully and then picks words, then we want to show you a longer word at the earliest possible opportunity. So this kind of macro behavior can be modeled in the hyperparameters of the system, and we can learn that by observing what the user does over time. Punctuation differs for different languages. We can use language detection to handle that. Okay, so how do we actually estimate whether this is any good? So remember, we're trying to estimate whether this is actually solved properly. The problem is that's actually very difficult to estimate. So in practice, what we do is try and come up with a number of different metrics that are correlates for what we're really trying to estimate. So we can simulate how accurate our top candidate is by artificially corrupting a piece of text and then running through as if the user was typing in that and see if we get the right answer. Keystrokes per character is KSPC. It's just a metric that people use in typing. And basically the idea is, on average, how many keystrokes does it take to enter a character? And we want this to be as low as possible. And then we can actually gather real-world usage statistics from our users. So this is just an example. We have some process that corrupts the text where we have the gold standard. And then we're going to run this through the engine and see how well it does at correcting the mistakes. And then we can do something like this, which is to say how many words were wrongly corrected, how many did we ignore that should have been corrected, how many were already correct and how many were corrected, and then we can compute metrics like precision over this. So this is kind of an odd example that we show execs in senior management at big companies to show how good we are. It's statistically horribly inadequate, but they don't know that. And this is another way of looking at it. Keystroke saving, this is the keystrokes per character thing. We've just coloured this in terms of when you just enter the word and when you have to prompt the predictor. So this is capturing that different style of typing. And again, you can compute, metrics against competitors and metrics against yourself to see how you're improving over time. I just want to finish by talking a little bit about user experience, because when you're a scientist, one of the things you can get caught up on is thinking about the numbers and how to quantify things and the maths and all that stuff. And you have to remember that ultimately, really what you care about is the experience that your users have when they're using your software. So the fundamental assumption that we're making is that this actually correlates with user experience in some way. And obviously, this doesn't capture everything about typing. So if I choose a pink theme for my keyboard, there's no variable in here that says anything about the color of the theme. So there are necessarily things that lie outside of the inference problem that's at the heart of something like this. So I've talked about this already, really, two different types of users. And you need to think about how different people are going to use your product and think about whether you've catered for those people. So one of the things that we thought about a lot, particularly in the early days, was what is this like as a user and what kind of things matter? So for instance, if I show 30 suggestions, I can get a fantastic keystrokes per character metric. But in reality, that's going to be a horrible experience for users because they have to read 30 words each time. So one of the key principles that we used right from the start was we want to reduce the cognitive load. So how much effort is a user going to have to go to? And this was why we changed from a ribbon type candidate bar to just 3 words where the buttons never moved, so you know exactly where the most probable word is going to be. So things like avoiding any character level UI changes. So things like making the keys grow, or when you're typing, that type of thing we steered away from. Try to allow the eyes to focus on a single location. It's difficult to do, but that's the ideal. and try to localize points of significant user interface change. And one of the main ones is avoiding frustration. It doesn't matter how clever the software is. If there are a few small things that annoy people, then that's going to completely overshadow how smart your underlying predictive engine is. In any product, it doesn't matter what it is. So you've got to spend a disproportionate amount of time focusing on removing those small frustrations. You've got to do annoying things like design themes for users. And it's amazing how, in terms of sales of SwiftKey, releasing new themes is one of the best ways to make more money. Which is so annoying because it's really not that interesting. But that's what it is. And that's it. Almost. Right, so you've got to treat your users well. We have this VIP forum where people can beta test and take time to understand what people are saying. And that really is it. Thank you very much. I think we've got sort of 15 minutes maybe for questions. Is that right, Thomas? Cool. So any questions now covering the whole thing?
Where is the bottleneck for you?
Yeah. So the question is, where's the bottleneck in terms of resource usage for phones? I would say that the major bottleneck, well, the two major bottlenecks are CPU performance, because latency is so important in this. So we have to provide a response to a predictive call within about 10 milliseconds. Anything larger than that, and the user perceives it as lag. So that's a major bottleneck. And then for a statistical model, the more statistics you can store, the better the model is likely to be. So memory is another huge bottleneck. So we're having to squeeze these models into sort of 10 to 20 megabytes, which compared with the sort of models that people are using to do this type of problem, it's really, really tiny. So really both of those things. Other questions?
Can you make a better prediction on a faster phone, or is it the system completely the same?
We could in principle. We don't, but you can. What's nice about working with probability theory is that the way you squeeze things is that you just make more and more coarse-grained approximations at each stage. And the other thing that's a major factor for us in accuracy is pruning. So we have to prune out a lot of the candidate space while we're going along. And on a faster phone, we can relax the pruning thresholds. Now, in practice, we don't do that, but we could, and maybe we should. It's a great question. Yep.
Another question. If you look on startups, I don't know if you consider you a startup or not. You can see that people are so into work. They kind of, for example, they're personalized. They are just working all the time, and they kind of lost their, young years. It's
Yeah.
the case or not?
Yeah. Good question. I mean, time has been very unkind to me over the last few years. I think people who build startups tend to be people who are obsessive by nature, and I think you kind of have to have that single-minded focus. Having said that, I don't think you have to completely, ditch your personal life. I mean, to give you an example, I think probably I've worked on average maybe 10 hours a day on this for the last 5 years, and actually that isn't too much. If you work in the city in London, you're probably working 12 to 14-hour days. So I don't think it's not necessarily so much about how much time you spend to it. I think in some ways you're much more likely to sell your soul if you go and become a trader or an investment banker or something. Having said that, what is the case is that starting a company is a bit like having a baby, in that it's always on your mind, and you never really get to forget about it, unless you're a very bad mother. So that's in some ways more of a pressure. It's just the fact that, you know, whenever you go to sleep, you're kind of thinking about it, and you wake up and you think about it. So hopefully that's some answer. Yeah.
Can you say something about bootstrapping the keyboard and then bootstrapping new languages, collecting data, all these?
Yeah, sure. So if you don't use any of our cloud services, then the keyboard will start to learn as you're typing, and that's fine. That works. That works well. This model here is the user-specific model, and so if you just start from nothing, then that has to build up over time. It's just going to take a number of weeks to learn. What we do is if you opt into the cloud service, then we analyze your historical text. And actually, we do this even if you don't for local text on the phone. So for instance, your SMS history. And what that does is, it's essentially, it pre-trains this model. So then that's going to be a better experience for you at the point that you start. And basically, the more data we can access that represents your historical text, the better the starting model will be. There isn't much we can do about this input modeling. That kind of has to be built up. But that will tend to learn more quickly as well, because the parameter space is much more constrained. Yep.
What technologies do you use? What language? Is written in Java or is written in C?
Yeah. So we wrote the core engine in C++. Because of this latency problem, we had to use something that was as fast as it could possibly be, and we spend a lot of time optimizing. You know, every time we introduce a new piece of functionality, we have to try and optimize it back down to where it was. The Android stuff is all written in Java. For different things, we use almost every language that's out there. So what we're particularly interested in at the moment is Clojure. I don't know how many people here have heard of Clojure. Clojure is very cool, and it's just kind of getting to the point where you can actually deploy reasonable applications. So we're quite interested in that, particularly for some of the newer, more experimental work that we're doing. But we've used Scala and Ruby and Python and Perl and almost anything else. Yep.
Do you have any data about that influence on your users? I think using the most common words again and again must shrink your vocabulary.
Yeah, that was an objection that we had quite a bit in the early days. And it's kind of settled down now. I'm not quite sure why that is. I mean, one of the arguments we always used to use is that you can actually use this kind of technology to insert suggestions of words that maybe people wouldn't use. So it kind of swings both ways. So if you always use the same thing in a particular context, it's very likely that we're actually going to suggest two alternatives that you could use in that context. In practice, whether people's vocabulary ends up sort of converging or diverging is something we haven't got data on, but it's an interesting question.
During the development, have you met a point where you have to say, oh, we did this completely wrong, or perhaps some new member came and said, yeah, this is good, but perhaps you could have it done 10 times better than that. So you have to start something from the beginning.
So at the moment, I guess actually probably that always happens, in the sense that as new techniques are researched, you should always be ready to say, okay, this has served its purpose for a while, but now we need to scrap it and start again. So actually, the company has, in some ways, been a consistent cycle of this. So when I first built the engine, when we then came to commercialize it, we had to basically tear it all apart and make it 10 times more efficient. And so recently we've been looking at a try technology, and there are some interesting new methods for compressing tries. So I think it's possible that we'll sort of completely tear that down. And the language model architecture, if we do move from engrams to neural networks, that will be another example of the same type of thing. But it's usually not because you've done it wrong, but just because things have moved on. Good question, thanks. Has one done here? Yeah.
I would like to ask, is there any chance that we can have SwiftKey one day on Apple?
So there are two problems. One is that the Apple platform doesn't allow for alternative keyboards, so we can't build an app in the same way. The other problem is that Apple don't want to pay us to use our software in their default keyboard. So if we could solve one of those two problems, then the answer would definitely be yes. What I will say is that what it is possible to do on iOS is to build standalone apps that embed the prediction technology, and we actually have a toolkit for doing that. So there may be some examples of that at some point over the next few months. Yep.
Sometimes I realize I type faster on my cell phone than on my desktop. Not when I code, but usually when I text to someone.
Yeah.
Is there any way to bring this technology to desktop user experience without being silly or something?
Yeah, it's a great question, and a question we quite often get asked. We haven't really found a way to do it, is the answer so far. I think on a smartphone there was such an obvious problem. You know, almost everybody is making mistakes, and it's the kind of thing that we knew would contribute to all users. I think on the desktop, some people are always just going to blaze away at typing, and anything that comes in the way of that isn't going to be unuseful. I think for a lot of people it actually would be useful. The question is how to do it from a user interface perspective without the kind of adaptive nature of a touchscreen. So we tried a few things. We built a Chrome extension that allows you to type in a similar way. We built an extension for MS Word as well. And I think we're still trying. I think the combination of not having found a compelling enough product and the market not necessarily being compelling enough means that we haven't got anything that's there yet. But it's a great question, and we probably keep trying. Yeah.
If you could go back in time, would you have done anything differently, like from the business point of view?
Yeah, I think I would have done quite a lot of things differently. I think one of the things that you learn, because this is my first business, you learn about how to hire people. And you learn a bit more about the type of people that you want to work with. So, you know, everybody in the company has contributed in a unique way. And I think many times the relationships that have been more difficult actually end up producing a lot of good in the long run. But if you could go back and do it again, you probably wouldn't choose to go through that necessarily. So I think just knowing how to hire effectively. And also, you know, we made some stupid structural decisions that caused various problems within the business that we didn't need to cause. And I think we would do that differently. I think it's, you know, the hardest and most complex part of running business is not this stuff, it's the people. And the things that I think we would do differently are related to people. So there are definitely some of them. Yeah.
Do you think that maybe one day there could be a movie about this? Like, jobs, you know, there's so many movies.
Yes, I think, yeah, if only Tom Cruise was younger, I would have him play. Maybe somebody like, I mean, the sad thing is that we have talked about this, but mostly only because we met Mark Zuckerberg earlier on this year, and watched The Social Network on the way out to kind of get in the mood. And it turns out he's quite a lot nicer in reality than he was in the film, but that kind of got us thinking, oh, you know, what if they did a film, who would we have? Maybe that guy, you know the guy who plays Eduardo Saverin in The Social Network? Andrew Garfield, he's pretty...
Do you know him?
That's sad. I'll get you his number.
He's dating Emma Stone, I think I have no chance.
And I think that is a brilliant question to end on. I can't think of a better one to say thanks. Great, I think that's it then, guys. Thank you so much for coming out.